Hello and welcome to section 4. This is Advanced Computer Vision Problems, and we'll start with the challenge of building a GAN for learning the MNIST dataset. So generative adversarial networks are pretty popular right now, and our goal here is to build a network that is able to learn a MNIST dataset. This is the dataset that contains handwritten digits, and we want to build generative adversarial network to learn this kind of dataset. So pause the video now and attempt to solve this problem, and in a moment I'll walk you through the solution. Okay, welcome back, and let's have a look at the solution. So GANs are pretty non-standard networks, and the first question that you have to ask yourself is that how does the GAN look like? And it has two main components. It has discriminator and generator. And discriminator pretty much just learn to distinguish between the fake images of digits and the real ones. And the generator tries to fool the discriminator by generating fake images. So those are two main components. Then what's the input and output for discriminator? And in case of discriminator, the input is real or fake image shaped as vector. So this is very important because the discriminator will get the data from generator from our MNIST dataset, and it will actually learn to distinguish between the fake and the real images. Okay, so this image is fake. It actually contains the real digit, the handwritten digit or not, right? So it's just 0, 1, fake or real. Then the next step is to ask the question, what's the input and output for generator? So this is our opponent. So generator tries to fool discriminator, and in the end they cooperate with each other. So the input is a single vector of noise data, right? So our input here is the noise, and our output is a fake image, and it has to be shaped as vector, right? It has to be a one-dimensional array. Then the next question would be, how should this discriminator and generator look like? What kind of neural network architecture should we use? And here we basically have two options. Because we're working with images here, we can use convolutional neural network or some kind of a multi-layer perceptron network. And in this particular solution, I've got the multi-layer perceptron example because it's a modular architecture and much simpler than the convolutional neural network, and you can train it really fast on CPU. But it really depends on what you're more familiar with. And then again, you have to keep in mind that in case of pretty much any convolutional neural network or multi-layer perceptron network, the end result is really the result of a lot of experiments. So let's have a look at the actual code here. And keep in mind that this particular example is optimized for working with CPUs, right? So it was specifically chosen because it gets the consistent results every single time, and it's really, you can train it pretty quickly on CPUs only. You don't need to GPU to actually train this kind of network. And also keep in mind that this is a very optimized version. It works really, really well. This is kind of the end results after a lot of experiments, so just keep that in mind. But the general idea is that in case of multi-layer perceptron network that can be used with MNIST, we can use a bunch of dense layers, which are fully connected layers, and basically just train our network that way. And our generator and discriminator will have this. You'll notice that those are pretty simple multi-layer perceptron network, but because they are optimized, they have tweaks here and there. So the general idea is to just use multi-layer perceptron network. So let's have a look first at our discriminator. So the input of our discriminator is the dense layer, and we have to specify here the input dimension, or what kind of data are we putting into the discriminator. And here we have to know what kind of dimensions your data have and we'll be using the Muniz dataset that will have the dimensions. Each image will have dimensions 28 by 28, right? So we have to keep that in mind when you define a discriminator, because it will accept fake or real images here. Yeah. So our output is this information about, we just using the simple sigmoid activation function and just one fully connected dense layer with just one hidden neuron. And this is basically the standard way of just when you have two classes. In case of our discriminator, we have if it's a fake, or want to train the discriminator to figure out if an image is fake or not, right? And we also compiling this architecture of cross entropy, which is a standard loss function for classification. And here we're basically training our discriminator as a classifier between fake and real objects. And what kind of layers do we have inside this particular network? So we have a series of dense layers with a non-standard activation function. So by default, dense layers have ReLU, or I think not by default, but most often for dense layers we are using a ReLU activation function. And in this particular case, which works really, really well, and it has been optimized really well, we are using an alternative activation function called leaky ReLU. And we also use dropout here. So as you can see, we're using those three elements consistently. So here's dense, leaky ReLU, and dropout. And we use it 3 times pretty much. And we end in with our last layer to classify our output. So this is a very optimized version of a multi-layer perceptron network that works really well with Muniz dataset. So let's look at our generator. So our generator, as an input, we should input the actual noisy data, which is just random pixels pretty much. And here we can choose the length of this data. And here we have just a vector of length 100. Then our output here is the actual length of the input of our discriminator, which is just this long vector, right? And this is the main idea behind the generator. It gets the input, noisy input, and it generates pretty much fake images. But then again, the next step is to actually train the generator so it can get better and better and at generating those very similar to the real images. The end goal here is to actually train generator, right? To output as realistic images as we can. So inside our generator, as you can see, our architecture is again pretty optimized multi-layer perceptron network for this problem. And we are using a sequence of dense layers and also leaky ReLU. And we are using 3 of those pairs. And this is pretty much just one layer because, as I said before, or most often we use in dense layer, those kind of problems we are using as activation function, we are using ReLU, and here we are using an alternative activation function which we have to define as a separate layer. And this is the main idea behind both discriminator and generator, and then we have to put it all together because those two networks have to cooperate. And the first thing that we have to define is that we want to freeze the discriminator at this point. And why we do that, you'll see in the training section. But the next step is to define the input for our OVLR GAN network. And we'll be using our GAN network, the whole combination of both networks, to actually train our generator. Right, so the first part of our end results and Gantt network is actually the input, and we are getting as an input, we are getting this noise. So this is pretty much the same as we've got with generator. Then in the middle, we have our generator, and as an output, we have our discriminator. And then we put it together using the Keras custom model, we can say, where we just define the inputs and outputs. And we just compile it with binary cross entropy. Just as you can see, this is the output is as a discriminator. It's pretty much the same as discriminator. And The only thing left us for define is to what kind of optimizer to use. And in this particular example, we are using Adam optimizer, and it's, as you can see, we have some hyperparameters here. And if you want to see how those parameters influence into the results that we've got, feel free to do that. Again, this example is highly optimized. So all those details are really after a really long time of experimenting. So we're pretty much using the optimizer, the same optimizer for pretty much all of the networks. Okay, so we've got our discriminator, our generator, and our overall GAN network ready to go.